Imagine, for a second, just standing in your kitchen or, stepping outside your front door. You look around and everything seems remarkably static.
Right, totally still.
Yeah, exactly. The milk sitting on the counter is just milk. The metal frame of your bicycle is just metal. Even your own stomach, sitting there doing its thing, feels like a static, singular object.
hmm
But that feeling of stability is a complete illusion. You are actually standing in the middle of this, like, massive, invisible magic show.
It really is the ultimate sleight of hand because underneath that macroscopic stillness, on a microscopic level, there is this frantic, continuous choreography of atoms.
Just constantly moving.
Exactly, breaking their connections, shuffling around, and making entirely new structures. The reality we experience is constantly, endlessly rearranging itself.
It's wild to think about. So today, our mission for this deep dive is to act as your ultimate science tutor.
We're taking you back to high school, but the fun version.
Right. We've got a stack of foundational science material covering chemical reactions and equations, and we're going to take those dense, sometimes, intimidating textbook concepts and translate them into the real-world transformations happening all around you.
Yeah, making it actually make sense.
Exactly. We'll break down the underlying mechanics of how substances completely change their identities. And we will finally demystify that infamous hit-and-trial method of balancing equations that haunts high school chemistry students everywhere.
Oh, the trauma.
Seriously. So, okay, let's unpack this. Before we try to do the cosmic accounting of chemistry, we need to understand what a chemical reaction actually is in the wild, not just on a chalkboard.
Yeah, because a chemical reaction at its absolute core is a transformation of identity.
Okay.
You start with your initial substances, what we call the reactants, and through the breaking and making of atomic bonds, they turn into completely new substances, the products.
But, we can't see atoms with the naked eye. So how do we actually know it happened?
Well, we have to look for macroscopic clues that this, microscopic rearrangement has occurred. We're looking for a sudden change in physical state or an unexplained change in color.
Like rust or something.
Right, exactly. Or the evolution of a gas, like bubbling or fizzing, or even a spontaneous change in temperature.
Which means we don't need a sterile laboratory and a white coat to see this happening. We literally see it every day.
Oh, constantly.
Like that carton of milk we mentioned left on the counter. If you leave it out in the summer heat, it sours.
Yep.
The bacteria inside produce lactic acid, which completely changes the chemical makeup. Or, grapes fermenting in a barrel to become wine.
Yeah.
That's a chemical reaction.
And digestion. The fact that you can eat a sandwich and your body doesn't just crush it up, but fundamentally alters it.
That's such a good one.
Digestion is a brilliant place to anchor this concept. Your body isn't just a biological blender. It relies on enzymes to actively break the chemical bonds within complex carbohydrates.
Dismantling them completely.
Exactly. Breaking them down into simpler, entirely different molecules like glucose. The sandwich you ate literally ceases to exist as its original chemical structure. It becomes the pure energy your cells run on.
So we know these transformations happen constantly, but I've always been fascinated by the sheer violence of some of them.
Oh yeah, some are extremely dramatic.
Like magnesium. You
Mhm.
take a dull strip of magnesium metal, maybe sand it down a bit to expose the pure metal underneath, and you apply heat. It doesn't just catch fire and slowly char.
Not at all.
It ignites with this blinding, dazzling white flame. And when the light show is over, that rigid, flexible metal is totally gone, replaced by a brittle white powder. Magnesium oxide.
To understand why that reaction is so violent, we have to look at what the atoms actually want. Magnesium is an element that has 2 electrons in its outermost shell that it desperately wants to get rid of to become stable.
It's just trying to offload them.
Right. And oxygen in the air around us is incredibly hungry for electrons. So when you apply that initial spark of heat, what we call activation energy, you destabilize the metal just enough for the oxygen to swoop in.
It just takes them.
Violently, the oxygen violently rips those 2 electrons away from the magnesium.
It's basically an atomic mugging.
It really is. And when those atoms snap together into their new, highly stable configuration as magnesium oxide, they drop into a lower energy state.
Oh, so they have leftover energy.
Exactly. All that excess energy they no longer need has to go somewhere, so it explodes outward as that blinding white light and intense heat. The identity of the metal and the gas are gone.
Just entirely replaced.
Yep, replaced by an ionic lattice that we see as a white powder.
That brings up a perfect visualization. I always picture this process like building with a massive bin of Lego blocks.
Okay, I like that.
You have this complex structured castle. A chemical reaction is basically taking that castle, breaking every single block apart,
Right.
and using those exact same pieces to build a spaceship.
Yes.
The individual blocks, the atoms themselves haven't changed. But the overall architecture, the identity of the thing you've built, is fundamentally new.
That Lego analogy perfectly sets up the single most important rule in all of chemistry. Because if chemical reactions are strictly a rearrangement of those existing blocks, it means we have a non-negotiable cosmic accounting rule to follow.
You have balance of books.
Exactly. The universe does not allow you to magically spawn new Lego blocks out of thin air, and it absolutely forbids you from losing blocks under the couch.
The law of conservation of mass.
That's the one.
If we start a reaction with, say, 5 iron atoms and 10 oxygen atoms on the left-hand side of our equation, we must account for exactly 5 iron atoms and 10 oxygen atoms on the right-hand side.
Right, the mass of the reactants must equal the mass of the products.
Which means anytime we write out a chemical equation, we have to balance those books.
And this is where the notorious hit and trial method comes in. And, if you were listening to this on your commute or at the gym, don't worry about visualizing a chalkboard full of numbers.
Yeah, please don't crash your car trying to do math.
Right. The goal here isn't to do algebra in your head, it's to understand the logic puzzle. So let's look at the classic scenario of iron reacting with water, specifically steam, to form magnetic iron oxide and hydrogen gas.
Okay.
Unbalanced, the skeleton equation is Fe plus H2O turning into F3O4 plus H2.
Okay, right away, the cosmic auditor is throwing red flags. On the left, we only have 1 iron atom, but on the right, our iron oxide has 3.
No problem.
And we have 1 oxygen atom in our water molecule on the left, but 4 in the product on the right. We have to fix this. And the standard method involves drawing physical boxes around each distinct molecule in the equation, right?
Yes.
So Fe gets a box, H2O gets a box.
And the absolute golden rule of the hit and trial method is that you cannot touch anything inside those boxes. You must leave the chemical formulas intact.
Okay, wait, let me challenge that for a second because this is where everyone gets stuck.
Sure, go for it.
If the goal is to get 4 oxygen atoms on the left side to match the 4 on the right, the most intuitive, easiest thing to do would be to go inside that water box and just change H2O to H2O4. Boom, 4 oxygen atoms. Why can't we do the easy thing?
What's fascinating here is that the physical laws of the universe actively prevent you from doing the easy thing.
Oh, really?
Yeah. Going back to your Legos, a water molecule isn't just a random pile of atoms. It's a specific interlocking architecture dictated by valency.
Okay.
Oxygen only has a specific number of slots available to bond with hydrogen. If you force an H2O4 into paper, you haven't balanced water. You've hallucinated a bizarre, highly unstable Frankenstein molecule that violates the laws of physics.
Wow.
It certainly isn't water anymore. You've changed the fundamental identity of the substance.
So changing the tiny subscript numbers alters the recipe itself.
Yeah.
If I want more oxygen, I can't change the nature of the water molecule. I can only change, like, how many entire water molecules I bring to the party.
That is the absolute crux of balancing. You can only add coefficients, big numbers, placed in front of your boxes.
Okay, that makes sense.
So to get 4 oxygens on the left, you place a large 4 in front of the H2O. You now have 4 complete water molecules.
But that creates a ripple effect. By adding 4 water molecules, I've solved my oxygen problem, but 4 times the 2 little hydrogen atoms means I now have a total of 8 hydrogen atoms on the left, and my right side only has 2.
The puzzle shifts, but you apply the exact same logic. You go to your hydrogen gas product on the right, the H2, and you place a 4 in front of it.
Okay.
4 times 2 is 8. Suddenly, hydrogen is balanced. Oxygen is balanced.
And we just look back at the iron. We need 3 to match the right side, so we drop a 3 in front of the singular Fe on the left.
Exactly.
So the final balanced accounting is 3 iron atoms plus 4 water molecules yielding 1 iron oxide molecule and 4 hydrogen gas molecules. Everything is perfectly accounted for.
It takes patience, a bit of back and forth guessing, hence hit and trial, but eventually the books always balance.
Okay, so we've figured out the cosmic accounting. We know we can never lose any of the atomic blocks, but that begs a deeper question.
What's that?
If the pieces never disappear, how do they actually decide to rearrange themselves on the fly?
Yeah.
There must be different choreographies for how these atoms interact when they actually meet.
Oh, totally. There are distinct patterns to how molecules dance, and we can categorize them by the type of exchange happening.
Like different dance styles.
Exactly. The most straightforward is the combination reaction. This is where two or more distinct substances crash into each other to form a single unified product.
Do we have a real-world example?
Yeah. If you take calcium oxide, commonly known as quicklime, and drop it into water, they violently combine to form a single new substance called slaked lime.
And if you're holding the beaker when that happens, you'll feel it get incredibly hot, right?
Very.
This is an exothermic reaction. Heat is rapidly exiting the system. And if we think about the energy states we talked about earlier, if the beaker is getting that hot, it means the new bonds in the slaked lime must be much more stable, and all the leftover energy is bleeding out as heat.
Thermodynamics drives everything. Whenever the energy released by forming new bonds is greater than the energy it took to break the old ones, the reaction will be exothermic.
We see this everywhere in nature too, don't we?
Oh, yeah. The decomposition of organic matter in a compost bin gets physically hot because microbes are driving exothermic reactions.
That's so cool. And the direct inverse of that would be the decomposition reaction.
Right.
Instead of two things combining into one, a single complex reactant breaks down into simpler pieces.
Yeah.
But if atoms fall into stable bonds because it's energetically favorable, they aren't going to just break apart on their own. You have to force them apart.
You absolutely have to pay an energy toll. Decomposition reactions are endothermic, meaning they absorb energy from their environment. You have to pump energy in.
Usually via heat or electricity, right?
Or even just light.
Oh, the light example is incredible.
Yeah.
If you take silver chloride, which is a stark white powder, and simply leave it sitting in a dish in direct sunlight, it will begin to turn gray.
Just from the sun.
Yeah. The actual photons from the sun are hitting the silver chloride molecules with enough kinetic energy to physically shatter the bonds holding them together, separating it into pure silver metal, which is the gray you see, and chlorine gas, which just floats away.
And that specific light-driven decomposition is the fundamental chemical basis for traditional black and white photography.
No way.
Yeah. The camera shutter opens, light hits the film coated in silver compounds, and forces that endothermic decomposition, leaving a permanent image in pure silver.
That is amazing. Okay, so we've covered atoms combining and breaking apart, but things get a lot more competitive when we talk about displacement reaction.
Go for sure.
Going back to our dance floor analogy, a displacement reaction is essentially an aggressive dancer cutting in and stealing someone's partner.
That's a great way to put it. A classic laboratory demonstration of this involves taking an iron nail and submerging it into an aqueous bright blue solution of copper sulfate.
Okay, so it's in the blue liquid.
Right. And if you let it sit, the iron atoms will literally forcefully evict the copper atoms from the sulfate compound, taking their place.
But why does iron win that fight? What makes one element a more aggressive dancer than another?
It comes down to a property called reactivity, which is governed by an atom's electron shell configuration.
Okay, getting back into the shells.
Yeah, iron's atomic structure makes it much more eager to shed its outer electrons and form positive ions than copper is. Because iron has a higher drive to react, it will outcompete the copper for the sulfate ion.
And what does that look like?
The result is visually stunning. The displaced copper falls out of the solution, coating the nail in this brown sludge, and the solution itself turns from bright blue to a pale green iron sulfate.
It's an atomic competition playing out right in front of your eyes.
Mm-hmm.
And if displacement is cutting in, double displacement is like two couples on the dance floor colliding and completely swapping partners at the exact same time.
Yes. That happens when you mix two aqueous solutions, meaning two compounds completely dissolved in water. For instance, mixing sodium sulfate and barium chloride.
Both start as clear liquids, right?
Exactly. The sodium and the barium ions are freely floating, but the moment they mix, the partners swap.
And the spectacular part of a double displacement is that usually the new pairing doesn't want to stay dissolved. The barium swaps over to the sulfate, and suddenly you've created this solid white substance that clouds the entire tube.
We call that a precipitate. The new barium sulfate compound creates a crystalline lattice so robust and tightly packed that the surrounding water molecules no longer have the strength to pull it apart.
So it just falls out.
It drops completely out of the solution as a solid.
Man, so we have elements combining, breaking apart by absorbing sunlight, competing for partners based on electron shells, and swapping pairs to form sudden solids. It's a chaotic environment down there.
Very chaotic.
But there's one specific dancer on this floor that is universally known for being the most aggressive, most problematic element we encounter daily. Oxygen.
Oh, oxygen is profoundly electronegative, which is just a fancy way of saying it is exceptionally good at stealing electrons from other atoms.
It's a thief.
A huge thief. And this leads us into an entirely separate class of chemical interactions known as oxidation and reduction reactions, or redox for short.
The terminology here always tripped me up, but the rule is surprisingly straightforward. If a substance gains oxygen atoms, it is oxidized. If it loses oxygen atoms, it is reduced. And because of the cosmic accounting we established earlier, the law of conservation of mass, those oxygen atoms have to come from somewhere.
Right, they don't just appear.
So if one substance is oxidized, something else must have been reduced.
Let's look at it mechanistically. If you heat copper powder in the open air, the oxygen molecules in the atmosphere aggressively attack it. They steal its electrons and bind to it to form a black crust of copper oxide.
Okay, so the copper was oxidized?
Exactly. But the beauty of chemistry is that it is often reversible. If you pass hydrogen gas over that hot black copper oxide, the hydrogen essentially steals the oxygen back.
So the copper oxide loses its oxygen, which means it's reduced back to shiny brown copper metal.
Yep. Yeah.
Meanwhile, the hydrogen gained the oxygen, transforming into water vapor. So the hydrogen was oxidized.
Yeah.
It's just a perpetual tug of war for oxygen.
It is. And if we connect this to the bigger picture, this electron tug of war is not just a neat laboratory trick. Oxidation is quietly, relentlessly destroying a massive percentage of human infrastructure every single day.
Wow. Through corrosion, right?
Through corrosion.
This connects directly back to the rusted cast iron pan
Wow.
or the metal frame of your bike. Rust isn't just like dirt accumulating. It is the slow, agonizing oxidation of iron. The moisture and oxygen in the atmosphere are actively stealing electrons from the iron atoms, forcing them into a brittle iron oxide compound that just flakes away.
And the economic scale of this single chemical reaction is staggering. Bridges lose their structural integrity. Underground pipelines degrade and burst.
That's expensive.
The automotive and shipping industries spend billions upon billions of dollars annually engineering specialized paints and galvanized coatings, simply to act as an electron shield to prevent oxygen from touching the underlying metals.
That's wild. And oxygen's destructive nature isn't limited to metal either. It's equally aggressive toward our food supply.
Let's talk about rancidity.
Oh, yeah.
If you've ever found a forgotten bag of nuts in the back of the pantry or smelled butter that's been left out for weeks, you know that sharp, sour, terrible smell.
It's awful.
That is the direct result of oxygen attacking the fats and oils in the food.
The mechanism is brutal. Oxygen molecules initiate a free radical chain reaction with the lipid molecules in the fats. It fractures their long carbon chains and creates highly volatile, foul-smelling new compounds like aldehydes and ketones.
The identity of the food has fundamentally changed.
Yes.
But human engineering has a brilliant workaround for this. Think about buying a bag of potato chips. Everyone complains that the bag is only half full of chips and mostly full of useless air.
The classic complaint.
Right. But if that were actually atmospheric air, which is about 21% oxygen, those chips would be completely rancid before they ever reached the grocery store shelves.
That empty space is actually a highly engineered chemical defense system. Snack manufacturers flush the bags with pure nitrogen gas before sealing them.
Wait, nitrogen?
Yes. Nitrogen gas is composed of two nitrogen atoms held together by a triple bond. They share 3 pairs of electrons, making it one of the strongest, most stable chemical bonds in nature.
Meaning nitrogen is perfectly happy keeping to itself. It has absolutely zero interest in attacking the fats on your potato chips. Precisely. By displacing the atmospheric air with nitrogen, they create a completely inert, oxygen-free bubble.
Oh, wow.
Without oxygen present to steal electrons, the oxidation reaction cannot occur. It completely halts the rancidity process and preserves the food indefinitely while sealed.
I will literally never complain about an empty bag of chips again. It's a literal force field.
It really is.
So, let's step back and look at the ground we've covered today. We started with the illusion of a static world and revealed that from the souring of milk to the blinding flash of magnesium, everything is driven by the desire of atoms to find more stable energy states. We unlocked the hit and trial method, realizing that because mass is strictly conserved, balancing an equation is just ensuring you don't invent or lose any of your microscopic Lego blocks.
We explored the thermodynamics of breaking and making bonds, the intense competition of displacement, and how understanding the aggressive electron-stealing nature of oxygen allows us to protect our bridges from corrosion. And, our food from going rancid.
It really provides a completely different lens through which to view reality.
It changes everything once you see it.
And as we wrap up our science tutoring session today, I want to leave you with one final, deeply provocative concept. We touched briefly on digestion earlier, but think about the broader process of human respiration.
Biologically, respiration is the act of taking in oxygen to break down glucose and fuel your cells. But chemically, it is classified as a continuous, finely tuned, highly controlled exothermic combustion reaction.
That makes you look at your own existence differently. If you zoom out far enough, a human life isn't just biology. It is an incredibly complex, interconnected series of billions of chemical equations constantly shifting and balancing.
Yeah.
And it demands the question, what happens to the delicate equilibrium of that cosmic accounting the moment you stop pulling in that oxygen?
Yeah.
You're not just breathing, you are actively fueling the most complex chemical magic show in the universe.